Whenever you're ready, Sean Hammond.
All right, so my name is Sean Hammond. I'm on a team with Rosh Patel, Jake Nashoff, and Chris Swindle. And we did a project on the resource usage of the security protocols and comparing them amongst each other from what we learned in class. So the motivation behind was that we learned how to implement and learned about these protocols in class, but we didn't actually learn the cost of these protocols in the class. And there were discussions in the class about how the Internet of Things is becoming a big security bottleneck and an unprotected part of the network. So we mainly wanted to look at ways for, say, IoT devices to pick protocols based on specific resources and implementing those into the network.
So we implemented the SSL in version 3, TLS version 1.2 using the Python 3 SSL library. For SSL and TLS, we used self-signed certificates. We also used the TLS AES-256 with GCM SHA-384 for the ciphers for both of these protocols. One thing we want to mention here is that going forward, we would like to try different ciphers along with adding a certificate signed by a certificate authority.
For the OAuth 2.0 implementation that we did, the implementation connects to a Google authoritative server to get granted an access token. And then with that access token, it goes to the Google API resource servers and downloads a file.
Now, even though the SSL and TLS protocols for the library in Python typipally use a Diffie-Hellman handshake for the exchange, we decided it would also be interesting to compare our own Diffie-Hellman implementation, thinking it might be more lightweight. And the three different variations that we compared were anonymous, which of course provides no authentication or security in the exchange. A server authenticated implementation, which uses a certificate authority signed certificate to authenticate the server, and then a station to station, which uses preloaded long-term secrets at each endpoint so that the endpoints are authenticated and secures against a man-in-the-middle attack during the exchange.
EKE, we did two implementations, regular EKE and an augmented EKE, which stands for Encrypted Key Exchange. There were no current libraries, so we had to code it from scratch. And EKE essentially requires a password to be exchanged between the client and the server, and that password is used to encrypt the messages being sent back and forth. So it has a similar idea as Diffie-Hellman, but with a password. And then the augmented difference is that that password is required to be hashed between the server and client, so it prevents a eavesdrop attack.
So we decided to measure both client and server sides of all the protocols. Specifically, we wanted to measure the connection phase and sending a file to measure the statistics and how the resources are being used. So for the connection, we did both for client connection and server connection. For sending the file, we had the server send the file and the client receive the file. The file sizes were 450 kilobytes, and the statistics that we measure we'll talk about in the next slide here.
So the measurements recorded throughout the connection phase and data transfer phase was CPU utilization, memory consumption, latency, DRAM power consumption, and CPU power consumption. For the CPU utilization, we use the PSUtil library. So the PSUtil library allows us to look at the CPU utilization of a certain process. So we created a watcher thread to watch all of these actions being performed, and then pulled these processes every 10 milliseconds to record the CPU utilization. For memory consumption, we use a library called tracemalloc, which allows you to start a meter, and then you're able to run whatever Python code you want and then end the meter. And it allows you to see the peak memory usage during those processes ran. And then we use the time library to measure latency. So we started a timer when starting the action, and then ended the timer when the action was finished performing. And then we just took the differences in those two timestamps.
Okay, so for the power consumption for DRAM and CPU, we use the PyRepel library. Similar to tracemalloc, this library has a meter which you can start before the function you're trying to measure and stop it after the function has completed. What this meter does is actually goes through the Linux kernel and monitors the process and the files associated with it for measuring the power consumption later on.
In the following figures here, you can see the measurements for energy, time, and memory usage for the client connect phase. We didn't include OAuth or EKE because their measurements were orders of magnitude larger, and this made viewing some of this data quite difficult. However, it is provided in the next table. If you look at the client connect, you can see that TLS and SSL use significantly less CPU energy and RAM energy, which was slightly surprising because we expected that the Diffie-Hellman, since it was a more simplified and lightweight protocol, would use less resources, but this could be due to some optimizations, low-level optimizations that we didn't include in our implementation. Interestingly enough, TLS, however, did use significantly more memory. And again, this could just be due to some differences in the implementation using SHA-358 versus SHA-256. And here we have the overall data, including OAuth and EKE. And you can see that their values are significantly higher than the other protocols.
So this graph shows the connection on the server side. It shows that Diffie-Hellman has a considerable amount higher energy usage rating than SSL or TLS. But on the memory side, TLS is significantly higher than any of the other protocols. I'm not exactly sure why the memory usage is so high compared to the other ones, but it does show that the power for the SSL and TLS are lower. And the numbers on the next slide, you'll see that OAuth is not included, and that is because OAuth was only implemented on the client side because the server came from a third party, and EKE did not have memory included in this one as well.
For this slide, it's showing the statistics for client receive. So this is when the client was receiving the file that was being sent from the server. So you can see from these graphs that the latency for SSL and TLS was actually significantly higher compared to the Diffie-Hellman protocols, which we think was due to the SSL and TLS using a larger MAC code. So it uses GMAC with the SHA-384, whereas the Diffie-Hellman used SHA-256 MAC. And then you can see for the energy, the SSL and TLS actually use more CPU energy and actually slightly more DRAM energy as well. And here's the data associated with it. So you can see again that OAuth was significantly higher in energy consumption and time. We'll talk about that a little bit more in the conclusion.
So for sending this file from the server side, you can see that the SSL and TLS use significantly less energy compared to Diffie-Hellman. It also is in the time versus the memory. You can see that SSL and TSL favored the latency more and used traded off with the memory there. Diffie-Hellman performed well compared to just any of the other protocols at the time was. One thing to mention here is that we think that the Diffie-Hellman used more energy because it was a custom implementation and not, it wasn't as optimized as the SSL and TLS. We'll see the actual numbers in the next slide here. Here again, we don't have the OAuth because it was just a client implementation and we used a third-party server to do the sending of the file. We also don't have the memory for EKE. That's about it. For the CPU utilization, you can see the average utilization for Diffie-Hellman was higher compared to the SSL and TLS and OAuth. Again, this is because we think it was for Diffie-Hellman, it was our own custom implementation, and we're using a different hashing method than the other optimized versions of the library.
So in conclusion, we found that TLS and SSL were typically the most efficient protocols. However, TLS did have higher memory consumption for the handshake process. It was interesting that TLS and SSL had higher latency on the server side for sending, which, you know, if you had a large server that was serving many requests, this might be something to consider. But if you're talking about IoT devices that are just trying to communicate with one another, it may not be that big of an issue. As was pointed out before, our implementation of Diffie-Hellman used more CPU power. And again, we think this was just due to missing some low-level optimizations. Picking the right security protocol is more and more difficult due to all the different protocols and variations out there. So we hoped that creating this guide and using these metrics as a form of measure would help people get an idea of what protocol might best suit their needs.
Thanks.
Thank
for
you.
listening.
Okay.